Swayam Prabha. Digital India. Educated India.
Good morning, all of you. Today we are going to start a new chapters. That's what is open channel flow. Is a just a application subjects what we learned so far on fluid mechanics. As you know it, we learned about mass conservation equations. We have learned about linear momentum equations, also the energy equations. As we have the three equations with us, as well as we also learned to use the control volume concept for the integral approach. So, today we are talking about those tools, those basic equations like mass conservation equation, linear momentum equations and energy conservation equations for open channel flow. It is very specific flow, open channel flow. This is the applications of fluid mechanics what we learned so far about the control volume, about these conservation equations, how we can apply it that once with a concept, with a some simplifications what we are going to do it. That is what I will discuss it. As the name implies it, this is what the open channel flow, that means we are talking about channel flow which is open. Okay. So, more details I will come it. Basically in this there are a lot of advanced level of open channel books are there, but I can suggest you to go through this FM White book which will be give it say very concise for the undergraduate levels, the FM White book. You can follow it or you can follow Senjal Simbala book, and if you want to have a go for advanced levels, okay, which is there. One of the course which we are floating it by me is river engineering. Okay. So, many concept of open channel flow we discuss about that, which we also followed open channel flow the books by Hanif Chaudhary. So, basically what I am telling you is introductory levels. So, we can read FM White book which is quite conceptually is concise book, you can read it or you can read the Senjal Simbala book. But as I said it, we are not introducing a new concept, whatever concept we have learned, how to use the control volume concept, how to use mass conservation equations, how to use the momentum conservation equations for open channel flow. Open channel flow if I talk about, I think almost all are familiar. Okay. So, because if you look at most of the rivers, they have the curved natures. Okay. Most of the rivers we have the curved natures, which is we call meandering rivers, meander rivers. But why? We don't know. We don't look at that much details. But in open channel flow, we can address that. Or when you have this is what the river. Natural flow systems. Let us come with examples like river flow. As you know it, river does not flow a straight path. So, it has meanders it as a curves. Okay, that is what is a river flow. And similar way you can see this natural flow systems which is very complex. Today's world we have Google Earth geovisualizers, you can see that how the complex river patterns. Okay. Anyway, we are not discussing that, or we try to make canal systems. Okay, for so you know it, we construct the canals or we construct the drain, the stormwater drainage systems, okay, which will have a more less, having a series of junctions, series of outlet. So, if you look at that, the flow can come this side, can go this side, this like this. Okay. So, if you look at that, there are man-made systems like canal, the drainage system, stormwater drainage systems, navigational channels. Okay, as you can look at that, the civilizations, how we made the best navigation channels to. So, that way if you look at that, these are all the open channel flow, open channel flow. Okay. One side we have a natural systems, okay, and another sides we have the man-made systems for drainage networks, the canal networks, navigational canal networks. So, if you look at that, there are a lot of systems we build it to transport of waters or any liquid, any solid waste through a drainage systems or the canal networks, okay, which is having a free surface. Basically, we are talking about when we have free surface. Okay. That means, if I take a cross sections, that means if I take a cross sections of a river or I take a cross section of man-made channels, okay, cross section at the 2 and the 1 If I take the cross section at the 1 as it expected, it is being a natural systems, it could have the free surface here, okay, for the section 1. Okay. So, this is the bed, this is the cross sections, this is the top width, this is what the top width, this is what perimeters, as you know it. Okay. So, this is the flow channels what we have for the natural systems, where the geometry may be the complex systems. Okay. But when you come it to the canals, like for examples, if I look at most of the times we canal, either you can see it any of the canals, okay, nearby. So, either it is a trapezoidal or a shape of rectangles. Okay. So, it will have the flow depth, it will have the perimeters, and it will have the top width. So, more details will come it. So, one is man-made, the cross sections, another is the natural process what is making this the shape of the cross sections of the rivers. The mostly what we are getting it, both the things, the common is the free surface, common is the free surface, there is a free surface is there. That means, at that locations the pressure is atmospheric pressures, because it is a free surface, the pressure will be the atmospheric pressures. So, at these locations pressure is equal to pressure atmospheres. This location pressure will be the pressure atmosphere. So, let me I just resketch it, the concept that means if I have a natural rivers and I have the free surface, okay. So, I can put it like this. So, this is the perimeters of channel, this is the free surface where the pressure is equal to P atmospheres, okay. P equal to P atmospheres, and here I have a man-made canal, okay, maybe carrying the water, maybe storm waters, maybe sweats, whatever be, okay, but it has a free surface. So, that is the reasons it is the pressure is equal to atmospheric pressures, pressure is equal to the atmospheric pressure. Same way if you can talk about that I have a pipe, but it is not fully, so it is half filled. Okay. So, if it is that the conditions, the pressure at these locations also comes to the atmosphere. This is what we can understand very easily when you have a free surface or open channel flow, the pressure at the top where the water depth start is, which is designated by these symbols, is a pressurized atmosphere. So, if that is the conditions, if you try to look it now, we have only the two force components with us now, because there is no pressure force, okay, because pressure is at the atmospheric levels, pressure is at the atmospheric levels. So, we have two forces, one is gravity force, second is friction force. That is two. Okay. There is no surface pressure force components. We will discuss more that, because there is a process. So, that is what the difference between the pipe flow and the open channel flow. In pipe flow, we have a pressure flow energy is there, but when we talk about open channel flow, we have the only two forces, one is the gravity forces, another one is the friction force. Where the frictions comes? The friction comes from bed or the perimeters, okay, bed or the perimeters. So, that means what type of perimeters I have, what type of roughness it has, the same similar to the as we discuss in case of the pipe flow, the roughness of the pipe flow, that is what we discuss it. The same concept will come it here, because of the presence of the roughness in the perimeters of a channels, it gives a resistance force, it gives a frictional resistance force. The frictional forces is given by that. So, that is reasons what type of the boundary, what type of the materials roughness is equivalent present here, that is what will give you a frictional force, and you know about the gravity forces component what will be there for the any flow control volumes. We can find out the gravity force, and we know what will be the frictional forces, because the friction force will come from the perimeters, and at these atmospheric levels there is a no there will be drag forces, but that drag force is much negligible. Okay. Air drag force will be much negligible compared to the liquid what we are considering. So, that means we nullify that. Not only that, as you know it, we have no slip boundary conditions. Okay. That is what we discuss in a very first class, no slip boundary conditions. The no slip boundary conditions imposes us the velocity near to this boundary will be 0. The velocity near to the boundary will be the 0. Okay. So, velocity near to the boundary, because of no slip boundary conditions, the boundary is fixed at the locations. So, the velocity becomes 0. So, you can now conceptually look at that we are coming to a very simplified problem, as we have solved many difficult problems in earlier classes like integral approach, the differential approach, but open channel flow is very simplified cases, because there is no pressure force components, there is a pressure is equal to atmospheres, the no slip boundary conditions when we are imposing it, the velocity near to the boundary, the parameters will be 0. So, since it is a 0, that means I can draw these the velocity distributions, velocity contours, okay, isovelocity contours. I can draw the velocity contours. I can draw velocity contours. That means maybe this velocity is equal to 2 meter per second, next maybe 1.5, 1, 0.5 meter per second. This is what the contours of equal velocities, that is what you can be, because near to the boundary velocity is 0. So, you can have a velocity distribution like, you can have a velocity for this case also we can have a velocity distributions like. That is what I always encourage you to just draw the safe, try to understand it, how the velocity distributions are happening it. Okay. So, if you understand that concept, that means you understand many of the things. Now, if you look at more introductions levels we are talking about, also we will talk about the classifications of open channel flow, hydraulic radius for some common sections, and we talk about the wave speed and flow proud numbers, which already we have discussed in dimensional analysis. Then maybe the next class will talk about other component like specific energy, the critical depth and all. But today class will be confining up to the wave speed. Okay, more details I will discuss on that. Now, if you look at, as I already said it, the basically we have the pre-surface boundary conditions. Okay, so once you have the pre-surface boundary conditions, if I remember it, basic pipe flow, when you are solving a pipe flow, that is the same things I am drawing it here. So when you have the pipe flow, okay, if you remember that we used to draw hydraulic gradient line and energy gradient line. Okay, that is what we used to draw it of a pipe flow of, if it is going like this, if it is a Z1 is a from a particular datums, that is what is datum head, then you have a pressure head, okay, that is what is P1 by the pressure head rho g, the pressure head, then you start hydraulic gradient, just top of that you start energy gradient lines. Okay, that is what we did it for the pipe flow, and that is the way we reflect the how the energy distributions losses are happening it, or how the energy gradients lines are there each point of a pipe networks with a very simple representations through energy gradient line and hydraulic gradient line. Okay. But now, when I am coming for the open channel flow, this is what the pipe flow. Okay. So, if it is that, if I have this, so this is my pre-surface in a pipe in a channel flow. Okay, this is channel flow. Okay, this is a channel flow having a slope, let be theta. Okay, having the slope of theta. So, I have the channel flow. So, if I consider a datum, that means my pre-surface will be the hydraulic gradient line. Above of that, I will have a energy gradient line. So, that pre-surface, whatever this is the flow depth, let be the y is a flow depth, z is distance from the datum. So, I have this, and this is what b square by 2 g, and you can have this kinetic energy correction factors. Okay, that is what you can see that. So, so that means the difference between the technical is between the pipe flow and this, one is flow energy is not there, the pressure flow energy is not there when you talk about the open channel flow. Because of that, your hydraulic gradient lines and pre-surface, they are the same, they are the same. So, that means whatever you line we are getting it the pre-surface flow, that is what is representing the hydraulic gradient lines. So, if I know the velocities, so I can estimate the energy gradient lines. I can estimate the energy gradient lines. That is what I can estimate the energy gradient lines. So, that is what I think, as I said it, the pre-surface is coincides with the hydraulic gradient lines, and the pressure is constant along the pre-surface, as I discussed the same way it is there. There is a no slip boundary conditions, as I discuss it, that the wall shear stress develops along the weighted parameters, which varies along the weighted parameters more detail. Okay, more detail, just let me explain it. That what it is telling is that when you have this, lately I have a natural systems, okay, having the river cross sections like this, okay, it is river. Okay. So, it is saying that no doubt the velocity at these points along these perimeters as a no slip boundary conditions will be the 0, and the flow is 3-dimensional natures, okay, 3-dimensional natures, as well as except very few cases like for example, for open channel flow, when you have very thin sheet flow maybe during the rainfall, beyond that all the flow, most of the flow turbulent flow, okay, turbulent flow, okay, except few conditions that the flow will be the turbulent flow, okay. And we will be discuss about that, what the flow characteristics in terms of subcritical, critical and supercritical. This is analogous to the supercritical. This is just analogous to the subsonic, supersonic and sonic conditions what you discuss about the compressible flow. So, same way incompressible flow in open channels where the gravity force dominates it, we classify the flow into 3 categories: subcritical, the critical and the supercriticals. As we discussed very beginning of dimensional analysis, we use the flow Proud numbers for classifications of these, like flow Proud numbers if is equal to the 1 then is a critical, if it is a greater than 1 is supercritical, less than 1 is subcritical. So, the basically we can have a different classifications of the flow. We will discuss more details why we need it subcritical, supercritical and the flow conditions, as well as let me what we are discussing is that we get the frictional forces, we get the shear stress, okay, acting over the surface, that is what the wall shear stress, okay, that is developed along the wetted surface, that is what is the part is wetted part varies along the wetted perimeter at a given cross section, that is what is a variability is there, as you can understand how the shear stress distribution there. And if I make it very simplifications that just want to put it for this one channel flow, if it is having theta slope, this is the bed level and I have the free surface. If I simplified it, okay, that is what we do it many of the cases, okay. The 3-dimensional flow which to approximate to the 1-dimensional flow. If I can approximate it, okay, that means we are just talking about that the flow is happening in these directions only, okay. Mostly this the longitudinal directions, that is what the flow dominating it, and if that is the region, see I have the velocity v, then I can say that v varies along these x directions, and if my y is the flow depth, so y also varies with a x directions, and the area of flow is also varies with x directions for steady flow, okay. For a steady flow, if I approximate it, okay, I do not consider other dimensions, that the velocity of the flow, the average velocity of the flow in the x directions, that is what is going to change it. The area of the flow is going to change it, the depth of the flow is going to change it, which is more interest for us. But if there is an unsteady flow, that means most of the times we also encounter the unsteady flow with a one dimensional approximations. We are that b, x and t, y, x and t, and area x and t. Okay. That is what we discussed a lot. Okay. So, it will come at a dependency function of the space and the time. So, basically the flow varies along the direction in most of cases. So, the velocity distribution in generally the 3 dimensionals, that is what I discuss it. The magnitude of the flow resistance depends upon the viscosity of the flow, as well as it depends upon the wall roughness, what type of roughness factors are there. So, the basic idea comes from this open channel flow, that is what let be because as I said it very beginning, this is very introductory levels with a very simplified way. I am going to deliver these lectures, but if you are interested for advanced level, anyway the courses are there in open channel flow, courses are there on river engineering. So, now let me I come back to that as I sketch it very beginning, that this is what when you conduct a lab scale experiment, okay, scale ends experiments, okay, any plume type of experiment, which we have shown the plume experiment in dimensional analysis and similitudes, the same continuing that. So, we can measure the velocity distributions in a open channel. So, you can have the instruments to measure the velocity. As you measure the velocities in any rectangular channels, as it expected it, the velocity of maximum velocity will not be at this is the lab scale experimental data. Okay. That is what I am emphasizes. Okay. This is what experimentally verified it, this is the distributions happens it. So, that means you will get it the velocity distributions like this, okay, velocity distributions like this. Okay. Again I am repeating it, this may be 2 meter velocities in terms of meter per second. So, this is 1.5, this is 1, this is 0.5, and along the boundary you know it, the velocity is equal to 0. Okay. But we observed from experiment that if is the y is the depth, then the maximum velocities occurs about 0.2 times of y, or 20% of the flow depth from the top surface. That is what the experimental findings. That is what the experimental finding about this velocity distributions. Okay. That means we can easily get the velocity distributions, okay, from velocity distributions from experimental data set. This is not a difficult. And since it is a turbulent flow, its velocity distributions will come from is a logarithmic velocity distribution, as we discussed in the boundary layer concept and all. So, velocity distributions also will follow the logarithmic velocity distributions. But what we are not worried about more about the velocity distributions of these classes, these 2 classes, what is that? More we are towards to understand it, what is the general natures of the flow. Okay. That means what we are looking at, that if I know these velocity distributions, which is from the experimental data, most upon things what we are looking at, that how much of energy losses happening it. Okay. That's what is our worry. Okay, we are not bothering about the velocity distributions, because anyway it is a open channel flow. For undergraduate levels, here we are talking about more details, that how much of energy losses happen as we estimated for the pipe flow. We have estimated using Modi chart and with a lot of examples we just demonstrated how to estimate the energy losses. Same way, if you have a network of open channel flow, then we have to try to understand it, how much of energy losses happening it for different conditions. Okay. So, one cases there are the classifications. One is a uniform flow, as we discussed for flow classifications there. I am not going detail. Now, if you look it as I discuss it, that we talk about natural channels, artificial channel and open channels. Okay. Its name of the open means one of the side is open. So, that is it is not having cover at the top. I think this definition is not without any cover, that definition is not that correct, but I will tell it that wherever you have a free surface, even if you have a pipe flow, if you have the free surface, that is the conditions is the open channel flow, it is not related to the covers. Okay. Anyway, that is maybe a simple way to explaining you, not going through this pressure is equal to the atmospheres and the pressure flow energy is not significant in this case. That is the reasons maybe it is done that, but let me not we have this, the cover does not matter it. Okay. We go for very simple cases like prismatic channels. Okay. Like many of the times when you have a man-made cross sections, okay, man-made cross sections, okay, we try to make it the same cross sections, okay, and the constant bed slope. That is what when you laying out a canals. Okay. So, mostly you try to make it the cross sections will be the same, okay, as well the bed slope will be more or less the constant. Okay. So, that is what the prismatic channels. Okay. Then we have the cross section directly proportional to any of the power depth of the flow. This is exponential channel, and if trapezoidal channels are non-exponential channels. Okay. That is basic definitions. Okay. Now, if you look at that, I think we already discussed about the steady flow. That means when you have a flow velocity, the flow depth, if it is a y, and discharge, energy losses, all either they are the function of space or the time. Okay. If it is unsteady flow, both it is having the both space and times. Like for example, it is a dam breaks. Okay. When a dam breaks happens, this is unsteady flow. But if you go the same distance you flow in a channels, okay, so we can after certain times of the transitions, then we will have the steady flow. So, steady flow is a very simple approximation what we do for open channel flow, but real life conditions when you talk about even if a channel canal flow or the river flow, mostly they are the unsteady flow. Mostly they are the unsteady flow, but we are approximating to making a steady flow. Okay, for but nowadays we have a for the river models like this, we have a Heck RSA. So, we can use detailed unsteady flow analysis, that is what is possible, but anyway this is bit undergraduate levels, and as I will tell it that how things are there. So, let me have a there is a two again simplifies is that the uniform flow. Okay. Uniform flow. This is what the depth, slope, cross sections, velocity all remain constant. Okay. So, that means all are the constants. Okay. That is what is depth, slope, cross sections, all are velocity, all are constant. How does it happen? If it is just happens when this sum of the force acting on the systems should be 0. like a terminal velocity of when you have free flowing object, you attain a velocity which is will be terminal velocity. The same concept. If you have a long open channel flow, there may be a stretch you will see that the net force acting on these control volumes becomes 0. There is no acceleration, no deaccelerated. Okay. Those the regions will have the depth, the slope and cross section and velocity will be constant. So, then the flow what we call uniform flow. So, basically it is a theoretically possible to have a uniform flow, but very rare case we can see it in natural conditions the real uniform flow, because attending the concept that some of the force acting on a systems is equal to 0, as I am explaining that when you drop a balls, it attains a critical terminal velocities. Okay, that is the same way net force acting on the systems is 0. That is what it happens it. The same way we talk about the uniform flow attains it when you have there is no significant change in depth, slope, velocity and cross section. Okay, that is very specialized conditions. Okay. Otherwise, you have the flow which we will discuss is non-uniforms, it varies with, and we also classified between two things is rapidly varied flow and gradually varied flow. Okay. So, if you just look at rapidly varied flow, that means rate of the change of any flow parameters is if it is very significant, very high order, that what is rapidly varied flow. But any of the parameter depth, the velocity, slope, if are not changing it, energy slopes is not changing that drastically, that abruptly. Okay. Very gentle change of these properties are there, then we call this gradually varied flow. As we discussed that mostly we have the turbulent flow, except the few of very rare case to have a laminar flow. So, that is what I am repeating it, very rare case we will have a laminar flow, very rare case we will have the uniform flow. Also some cases we can simplify the steady, otherwise the flow what we consider it all its flow unsteady, turbulent, okay, non-uniform, and also we talk about maybe mostly it is also the subcritical flow we design it. So, basically what we are looking at unsteady, turbulent, non-uniform and the subcritical flow. That is what is the basic classifications of most of the flow in open channel. Now, if you look at a very simple cases to classify between all these flow systems, again I am to sketching this part. As I said, it is very long channels is there, then is a drop is there, then we have the channel. Okay, so that means sometimes we do it. Okay, to change the slope in a canal, we make a drop here. This is what the drop structure. Okay, so it is a drop structure. If it is a very long canals, we may be attending a uniform flow. Okay, uniform flow UF. So, as I discussed earlier that these are the flow conditions where a net force is acting is 0. So, that means the gravity force and the friction force both are equal each others. That is what you can happen it in case of uniform flow. As there is change of the grades, okay, from these two slopes, definitely you can understand it. If I make a free streamlines of a free surface flow, I will have a flow comes like this, then it will have a flow like this, then it will have a this type of things. Okay, just flow will come like this. So, if you look at that, this is what uniform flow. After that the slope is changing it, but very gradually. As it is changing in gradually, we said gradually varied flow. That is what, that is the gradually varied flow, but that means the flow depth, the velocity, our basic parameter of the flow is the depth, velocity, all these terms, they have a functional relationship, but that variations are low, gradually changing it. That is what it has there. Then gradually it is a changing that part. So, we can classify it as a gradually varied flow. But after that, if you look at the slope has changed and there is could be a formations of hydraulic jump, we will talk about that in later on. Okay. So, there is some sort of jump structures will come it as the flow is there. So, that is the reasons we will have the change of your velocity is very rapidly. So, that is what is rapidly varied flow. It is very rapid. So, if you look at the V, the H is very rapid. After that again you can have a gradually varied flow, or you can come to the uniform flow. So, that is the flow patterns. So, the basic idea again I have to tell it that please sketch like a streamline. You are used to have it sketch the streamlines for any flow patterns. Similar way, when you have a interactions between two any open channel flow, try to sketch the free surface lines. Okay. If you can really sketch the free surface line, then you can understand the flow, how what type of flows are happening it. Exactly the same way as we discuss about the stream flow, streamline drawing, what we used to do it. So, on open channel flow, we should draw the free surface lines, approximate free surface lines. So, if you can draw the approximate free surface line, we can understand it where your uniform flow happens, when which is the regions the gradually varied flow happens, which are the regions the rapidly varied flow happens, gradually varied flow, then uniform flow. So, you can have a approximations of this flow in the three category. So, that like for example, of uniform flow, we can easily understood it, because this is a there is no acceleration, no deaccelerations, no change of the flow depth, no change of any of the flow parameters characteristics. That means sum of the force is equal to 0. So, this is a very simple cases. We can solve it to equate the basic parts. Okay. Sum of the forces is equal to 0, that means gravity force is equal to friction forces. But if you look at the gradually varied flow, and this is also we can simplify it for rapidly varied flow, but just we have to classify the flow as we used to do it for any other cases like subcritical, critical, unsteady, steady. So, in open channels we classify uniform flow, gradually varied flow, rapidly varied flow. Okay. That is you can with respect to the change of these flow characteristics, the velocity, depth, energy slope, the shear stress, okay, all if are changing it, okay, and what is the rate of the change with respect to the space. If I define it, that is what we are defining it: uniform flow, gradually varied flow, rapid flow. Okay, that is I think you could understand this is very easy things. As I said it earlier, we have gone through very complex subjects. This is very easy subject for us now. Again the definitions what it says that just rapidly varied flow, the flow depth is changes markedly over a relatively short distance in the flow directions. So, that is a flow past a open gate. That is what it happens is that if you have a gate in a and you are just lowering a gate, okay, that is what you are doing it. As you are lowering the gate, if this is the free surface, so there will be rapidly varied flow and there will be a hydraulic jump. We will come into more details. Okay. So, there will be the flow change. So, these are the regions we will talk about the rapid varied flow, but these are the regions where we can talk about gradually varied flow, followed by you will have a gradual varied flow. This is what we have the free surface. That is what is we have the free surface. That is what I am just sketching it. So, as you are gradually varied flow, the flow depth changes gradually. That is what is of a long distance along these channels. Okay. So, this is a gradually varied flow. That means this distance is much longer to change of the slopes. Okay. Follow typically rapidly varied flow and uniform flow. So, it is a like we call about laminar boundary layers and turbulent boundary layer transitions. The gradually varied flow happens intermittent between a rapid varied flow and the uniform flows. Okay. Basically, we are talking about, because as I said it, we made it a very simplified case of one dimensional case, okay, which I think is some 90s, 20s or 30s. Okay. These concepts are well built almost 100 years back. Okay. That is the reasons. I do not want to focus more, but let me as a text you have. But now we have a technology with us. It is not like we talk about the cases which are very simplified cases, but just trying to highlight it that 100 years back there was no computers. So, methodologies were more a conceptual framework. Now, they have introduced a new concept to look at that. One is called hydraulic radius, because as I sketching these different cross sections. Okay. Because in pipe flow you may have the circular or this square pipe flow, but in natural rivers, in case of different canal structures or drainage structures. So, we need to have a hydraulic radius concept. Okay. So, if you look at that, a simple concept of hydraulic radius. Okay. That means is A by P. P is the weighted parameters, excluding the top surface, which are the surface which is the free surface. If you excluding the length of that. So, area is the area of the flow cross sections. Okay. That is what is it is equivalent to a meter dimensions. Okay. You can just put it. Okay. Is a radius, we define it A by P, A by P. So, what does mean by that? I just have a very simple examples, that if I have a rectangular channels, y is my depth and b is my width. Okay. So, area will be simple things, area will be b into y. Okay. So, simple geometry. Weighted perimeter P will be b plus 2y. So, y from this side as well as y from this side. So, b plus 2y. So, hydraulic radius will be the A by P, which means the b by y, b plus 2y. Okay. So, b by y by b plus 2y. If y is much less than the b as compared to a river systems, okay, b is much larger, maybe around 200 meters or 300 meters, y will be 3 meter or 4 meters. If you have that the conditions. So, that means this part can become 0. So, r will be close to the y, okay, close to the y. That means, if I extend the b, okay, making more and wider, my radius will be the only depth. my radius will be the only depth. So, you try to understand it. If I just make a wider, okay, my radius will be only the depth, that is what is converting it. So, that is a simplified hydraulic radius we are propose it for a open channel flow, because that is what is because we are synchronized with our power pipe flow. So, to make it the similar type of concept, okay, that is the reason the concept of hydraulic radius has come in, because always having in mind that we are trained for the pipe flows. Okay, that is the reasons we want to have a edge equivalent. The open channel flow, we are making it edge equivalent to the pipe flow. That is the reasons we introduce a hydraulic radius, okay, which will be the area by the weighted parameters, and as becomes wider and wider, the hydraulic radius will become closer to the depth. That means you can draw an arc, okay, of r, y, that is what is equivalent, the radius is given to us. So, if you trying to this, because we always look it to find out this characteristic lengths, okay, that is what is we need to compute this Reynolds numbers of the flow, that is needed rho v characteristics length. Here we consider the hydraulic radius by this mu. So, this is the characteristic length. Okay. For edge equivalent to the pipe flow, we have using the d. So, we are not using the diameters of the pipe, we are using the edge equivalent, edge analogous to the pipe flow, we introduce a hydraulic radius concept. In the hydraulic radius concept, we use that is to estimate the Reynolds numbers. Most of the times, just your things, well, you say that flow is turbulence, okay, do not talk about is a laminar flow, the flow Reynolds numbers is goes much beyond the critical Reynolds numbers of the open channel flow is 500s, okay. As equivalent, the hydraulic diameters when you put it, again we are putting in 4 times of, okay, that is the reasons, please do not have a confuse with diameter and radius should have a 2 times, but edge equivalent as you have put it, that is the reasons 4 is coming to here. Okay. So, diameter is a 4 times of this. So, that is the reasons in a pipe flow you know that the drivers, the critical Reynolds numbers to define the turbulent flow is the 2000, but for open channel flow we have the critical Reynolds numbers is just 500, because you can make it the 4 terms is there to make it equivalent reference. So, we introduce a new concept of hydraulic radius, hydraulic diameters as to make it the pipe flow and the open flow are the similar type, okay. To analyze this, many of the undergraduate course questions they ask basic things, even if your GATE or engineering service, okay, how to estimate weighted parameters, where to estimate the area, what is the R and what is the diameters. So, this is a simple for a different geometry, you have a at the Clan strength levels you know it for different geometry, for different depth you can always estimate it what is the hydraulic radius. This is what I was talking about, that when you have a thickness you will come to the y. In a circular channels you can express in terms of theta, that is what angle theta, and you have a radius r. So, you can represent weighted parameters, you can area of the flow, then you can get the hydraulic radius. That is basically theta representation. Same way we are looking at theta part is here to defining the hydraulic radius, what will come it in terms for a trapezoidal channels, which is includes the weighted parameter of this as well as this, and we try to just find out the hydraulic radius or the hydraulic diameters, okay, for different flow geometry. These are the questions, I think it's from GATE questions, which is gives us that to estimate, find out which is the different flow channel with a different sections, okay, circulars, rectangulars and triangulars, trapezoidals, and you have to find out which stem in terms of hydraulics radii. Okay. I think it's not a big issue, and always you can compute hydraulic radius, and finally you find out the solutions, what will be the 4, 1, 2, 3. Okay. So, it's a very simple things, just to have to understand that to estimate the area, flow, perimeters, and estimate the hydraulic radius. Okay, so with this, I conclude today's lecture. Thank you.